Hello. Good morning.
Good morning.
Any question so far? No.
I was mostly just wondering if you'd be able to go over both assignment 5A and 5B, since we won't have class on Friday.
Oh, okay. 5A and 5B. Oh, there are two programming assignment this week. Yeah. One is differential kinematics. Okay. So this one, if you look at it, is pretty much the same as the just use the function that we give you. That should be enough. One moment, okay? Sorry. Differential kinematics. When I try to create this course, I create probably more than 100 PDF PowerPoint files, quite a lot of them. Spend with me a lot of time. Okay, so this one is pretty much apply this equation should be enough here. It is the same problem that you see here. You said that the speed, the angular velocity is different. Here is a 2 radian and the homework is 3 radian, right? And then the coordinates movement is different. Is okay? And you use this one should be okay to solve the problem. That's it. So just different number, but almost the same equation. Does that make sense? So
Yes, it does.
So this one actually is the one you see here. It's actually this video. This video has an equation. Okay, this video has an equation. Video on top of it has an equation. Okay, is that okay? And this one, last time we explained it already. So it basically uses this V equals theta. That's actually the rotational velocity times the transitional velocity times the W. The equation is where? Is this one. It actually is right here. We actually talk about it right here. There is the math behind it. How we derive this metric is over here. Okay. So the video eventually here the velocity is this one. Rotational velocity. This one is transitional velocity, and then the speed in the original frame. I'm sorry, it's in the frame of the observation. Is that okay?
Yes. Yeah. Thank you.
So just use that formula, it should be fine. And for the theory, you need to study the whole thing here. Okay. You need to study the whole thing here. Okay. And this one, I'm sorry. So this one is like that, and then let's see. We find material. Let's look at the week 4. V4 kinematic, this one instruction material. Here there's lab. Let's see, this is the V4 lab. Okay, differential. Okay, I'm sorry. If you need a PDF, is there a way that you can download a PDF? Let me see. Is there a way? I believe that you have a way you can download a PDF. Let me give you the PDF then. So let me give you this files PDF. Okay. I'm not sure. There should be somewhere built in the course to have this PDF, but let me check. Okay, there's a PDF. Okay, let me actually attach the PDF to you. Okay. Let me see. Actually, doesn't allow me to attach a file. Okay, I'll send you email. Okay, I'll send email right away with the attachment. So message. I'm going to send to you. So you right?
Yeah.
So here, let's have attachment. Because I'm not sure other students need it or not, so I don't want to create too much garbage email for someone who is not interested. Okay, let me see. This one is visual kinematics. Okay, set. Okay, if you have further question, let me know. Okay. If you have other question, let me know. There are students have many questions, just asking mostly about homework. Okay. So let's see. Another one is okay. So for the 5A is something like that. It's actually basically try to understand the differential kinematics and then put the equation into work. So programming assignment B. This one is gonna be Hardenberg dynamics. Okay, there's a programming of the. This one also you need to look at this video for how the Denby-Hardenberg matrix can be done. So you need to find the appropriate lab materials. Okay. So here, this one you do have this Denby-Hardenberg matrix. So let's see. Let's look at the. Okay, so Denby-Hardenberg. So let me. It probably is in week 3. Okay, so the homework is actually not as fast. It's a little bit lower. Okay. So here you do have the homogeneous transform matrix. They are sample code. So be aware of these sample code. You can download the sample code and do the reference from there. So right here you have the homogeneous transform matrix. This one I believe do have the sample code for HTM there. And then the Hardenberg one. Let me see, these are the labs. Kinematic. Let me, so you search around different labs. Okay. So those labs actually give you the sample code, actually. You know what I'm saying? So different labs. See, this week 4 lab. There's a zip file. Those zip files usually are the sample code. There's a PDF, that's a PDF you need. And then there's a zip file. Zip file give you the sample code. Is okay? So let's look at this zip file, say. So you go to here, kinematic, right? So this one is a course over there. So let's actually go to this website. This is my GitHub site. So all the simple code and PDF is over here. Okay, I'm sorry. I actually find it now. Wait, something wrong with my keyboard. It doesn't respond. Let me see. Okay. Do you hear me?
Yes, I can.
I'm not sure what happened to my mouse. I'm trying to click in it. All my computer is super slow right now. So you click the lab and there are some zip file you can download, but those are sample code you can download and start it from there. Modify it a little bit. Is that okay?
Yes.
So every lab I do have those sample code. So I'm not sure. Some students still don't get it. This course I do give a lot of code in there, and you can just try to learn from there. Number can be different, but the basic programming is the same. I'm sorry, something's wrong with my keyboard right now. It's not working. Yeah, I'm not controlling my computer actually. Since it's not my keyboard, it's actually my computer. My mouse doesn't respond at all. Okay, I'm using touch panel. Actually, it work. My touch panel is working. My mouse is not working. Okay, let me check my battery. One moment. Okay, sorry for that. So basically, use the link and then use the link. And you can go to the GitHub site, and the GitHub site will give you the PDF and a lot of things, the simple code. Okay, it's back. Okay, sorry for that. Okay, so right here it's back. So right here you see this one is the undergraduate course. I call it CS74. That's my own. Okay, it's nothing to do with the school. So here you say Unit 2 is kinematic. There's a lot of PDF file you can download from there. Okay. So this one I'm pretty sure I can copy to you. You can just go here to check all the PDFs. And also the simple code. Okay, one moment. Simple code. So kinematics, these are the PDF. Simple code is in the center already. So you can see that they are Unit 2's simple. I'm preparing this one for if there's a chance that I need to teach undergraduate course. So I said that it's a 74 thing. So your Dennerby-Hardenberg should be this one. Is that okay? Homogeneous. These are the simple code you can download and extract it. Do you know how to uncompress, right? Zip
Yes.
file. Yeah, this one you download. Here you say view raw, okay, view raw, and then you download to your local. And then there's a zip file. And you should be able to unzip it, and then those are the code. Those are the code you can have. So right here, going to the directory, here is a Dennerby.py, right? Is okay? So you should download a lot of code to study. Okay? So I give you the link in the chat box. You can copy it down now, okay? This one, the whole unit 2. Other unit, you go back to the top of here, they are by the unit 1, 2, 3, 4, right? Different chapter. Is that okay so far?
Yes.
Okay, but the details things that I cannot repeat again because that's a whole theory of what is Sternberg-Hardenberg thing. You have to watch the video, okay? Detailed stuff, there are a lot of things that I don't go back to explain it. It's the same. If I continue to talk about it, it's the same, okay? You can watch the video. And key points, those are sample code. You can study from there. You can study, okay? Any other question? So every week, you are supposed to come here, watch the video for the lecture. And then before you work on your homework, each homework there is a regular course video and this undergraduate levels video as well. And this one, if you find that you need a sample code, you have to find maybe the previous chapter or previous lab, there are sample code there. You can hide it somewhere, okay, hide it somewhere in the course. You just check 1 week, 2 weeks back, and there should be a file for you. If you cannot find it, then you just go to this GitHub site. This GitHub site actually is what my collection of the course. I do have some more material, including the Java, Python, C++, okay, web programming. And this one is all the courses I teach in Louis University, you see. I use a church as the Louis symbol. So the programming language is also here. CS46K1 also in here. It's okay. Only those one with the yellow mark, that is not complete yet. Okay, this one's still under construction, but there are some material. So this one, 74, this one is the one that you will need. All the PDF and the zip file are here, okay? I have my GitHub open to everybody. If you need a Python coding, it's the same thing. You can come here to look at some of the Python codes that I teach. The PDF files. Is it okay? So I teach tons of the courses. And you can always come here to get it. Okay. These are resources you can find. Java, section Java, I teach several Java courses, C++ course. Any question?
I actually have another question about assignment 3.
Assignment 3?
Yeah.
You already got bothered for quite a while.
Right. I'm
Yeah,
still.
what happened? What happened there?
I was just I'm still trying to figure out how to use the extender. I was looking at it again this week, and
So the thing is like this one is a Scala manipulator, right? So this was based on this, okay? And which part still bother you?
I guess like how to do the Python code to add in the extender. I think I understand like modeling it in like a matrix, but in regards to
Python code, you do not have much to. For the extender, actually, it's easier than the revolute join. Okay, so basically, when you have an extender, say, if you don't have the rotation, then your rotational part is identity matrix. You just put the extender there. That should be enough. So let's go back to the model. Okay, so your rotational metric is right here. You do 1 0 0 0 1 0 0 0 1. Okay, 0 0 0 okay, 1. So here, this one is your displacement vector would have, right? And here you do have your SYG 1, right? And this one is your X1, your P1. Your P0 is here. You want to try to find this one, okay? So there's assumption you will put over here. That's your displacement extender portion, right? So let's assume that you actually, this is a metric. So let's assume only G you do have extension. So you will be actually this one times this one. So the D will happen on here. Only you pick up D if you see the D. You're affecting your G. Okay, you're affecting your G because this one times this one, you only have the G plus D. So your G becomes G plus D. Right? If you look at these two terms. And the other term you do have X1, Y1, and 1. Okay, so only this one you actually grow by D. Right? Math-wise, let's look at just mathematically. Don't think about the join or whatever. Just look at this mathematically. It's okay. Hello? Do you hear me?
Yeah, I can hear you. Sorry, I was just
Okay.
thinking.
Yeah, so mathematically only G has a change by this one, by the red one. This row multiply this column. This row multiply this column. You got G got change. Right? Is that okay so far?
I think so.
If this is okay, let's go back to the model, right? You do have an extender. This one changed by D this way. And this is your G direction. Right? And then let's assume that this is this point is your new point. Let's assume that SYG is all the same. There's no orientation problem. The SYG, everybody is the same. So there's a D change over here. Your coordinate this side would actually what? So here originally, if this point originally is G, but it add a D. So with respect to the reference point here, is this one actually G0's coordinate should be the G1 plus D. Right? Because this one you move by D over here, you actually move down by D over here. Right? You extend by D, right?
Right.
There's no orientation, no change of the coordinate, no rotation. Under that condition, that would be like that, right? So that should be pretty clear. For your extender, it's just purely the rotational part. You don't put to put energy just identity matrix and then 0 0 0 D. And time use X1, Y1, G1, 1. Okay, you will get your X naught, Y naught, G naught, 1. Right? This metric is for, let's assume that there is a extender here. Right? The friend is right here. Right? And then there's a tension of D. So let's assume that this D is 0 right now. Then your N effectors friend is overlapping with your observation friend. two are actually overlapping. If D equals 0, right? And then if when you go for D, then your D will actually become this one. Your friend actually moved by D, right? But to this point, to your end effector, this will still be origin, still 0, 0, 0. But if you observe from up here, it actually have extra D that you observe over here, right? Is that okay?
I think I get it. Yeah.
Yeah. So that's the extender's calculation. Okay. That's it. And if you do have rotation or orientation, that's a totally different story. You just change the rotational metric here. That's independent of this extender. Any rotation is over here, and your displacement is over here. These two are totally independent things. There's no need to worry about the rotation. You just put the number for rotation over there. Okay. Does that make sense now?
I think it does. Thank you.
Yeah, yeah. But you got to understand this, okay? And better way to do it, you actually can check the sample code. I believe that well, maybe not the same, but you check some of the code may tell you how to do coding there. Is that okay? The CS74, this one. Each unit do have some code here. Unit 1 is introduction, there's nothing. Unit 2 is all of the kinematics. So here's a lot of simple coherent homogeneous transform metric, okay? Displacement vectors and inverse dynamic, okay, and general Jacobian, they are all there. Okay. And then here same thing. Here you do have sensor vision one. They are also in different unit. Okay. Okay, what other question? So far are you okay? If not, it's week 3. Are you behind or are you okay so far? Try to don't pile up too much things. The last week is you cannot do too much. So try to speed up a little bit, okay? And usually the week 5 starting for the after this transform, the sensor portion pretty easy, okay? Primarily is this kinematic part is more difficult. Okay, so we exercise more on the kinematic parts. Okay. Any other question?
I don't think so.
Okay. And 5B, this one is a Denby-Hardenberg metric. You just have to follow the Denby-Hardenberg's iterations algorithm to find the Denby-Hardenberg. This one, last time we talked about it already. So it is the determination of the Denby-Hardenberg. You have to figure out how to extract the parameter theta, alpha, d stuff. Okay, how to create this table. That is something you need to learn. Okay, this is something you need to learn. And again, the video, I think we had discussed this before. Okay, and the math is in here. The whole math is in here. Okay, even Python coding, you have the simple code that can help you. Okay, just need to download the right simple code. Friday morning, I'll still be here. Okay, even though if you don't show up, I'll still be here briefly if somebody still have question. Is that okay?
Yes, thank you.
I'll still be here. I'm okay. I don't go Black Friday shopping. I never go there. Some people do want to get the TV or something, but I don't. Okay. Okay, you don't have question?
I don't think I have any more.
Okay, and this week, we have two things. One thing is in the teaching part. One is the trajectory planning. The other one is the sensor. So let's cover this part a little bit. Okay, the projective sensing, projection planning. So this one basically is to we talk about inverse kinematic, inverse differential kinematics. Okay, so it's talking about when you got the desired path, how you control your robot. Okay, so in the past we always talk about how to use CEDA to control your robot arm. So now we use the inverse kinematic to do prediction and estimation to figure out how we can move our robot to the target location. Okay, so trajectory planning. So trajectory planning, trajectory generation, figure out the velocity components of the end effector's motion along the path. There's two things. One is the path. One is the trajectory. Trajectory and path are two different things. Okay, so you can say that there is a path from point A to point B. Say point A is 1, point B is 5, 5. Right, so this one is a path. Path only say that this is a path from San Francisco to Chicago, right? So that's actually is a path. Path is just saying that from point A to point B. Okay, and you can go different way. Right, you can go different way. And the real road that you go to, that's your trajectory. Okay, real road that you go on is your trajectory. And this trajectory actually can be, X can be a function of T. Y is another function of T. So along the time, for different time, you do show up at different location, X of T, Y of T. Is okay? You're driving your car there, but the velocity is different. So this one is a parametric function. Does that make sense? Okay, so you need to control your X and Y so that it follow a certain path. So it actually is a function of the X and Y. X and Y is your workspace variables, right? It's your workspace variables. So basically, you need to control your CEDA and your B to maintain it. So you actually will go from point A to point B, and then at a certain speed along the path. So the black one is the path. The real road that you go on is your trajectory. Okay, so when we shoot the missile, right, from a ship, there's also a trajectory. When we shoot a cannon gun, it's the same thing as a trajectory. at how much time you will travel and where you will hit is something you want to control, right? It's something you control. So path only talking about the starting point and ending point. As for how fast we go on it, that's actually it's a trajectory generation. Okay, so first one you need to know about the parametric equation. So we had 2 points, point 1 and point 2. And we go from point 1 to point 2, right? There are several different paths, and you can create a x of t and y of t. So x is the parametric function, the parameter is the t. Right? Different time you show up at different x and different y location. Is that okay? Is that okay?
Yeah, I think so.
So your dt is actually distance or displacement vector is xt, yt, x0, y0 plus abt. AB is your speed. Okay, it's your speed. Okay, AB is your speed. Okay, you can use a different speed for it. Okay, whatever. Okay, you can take the equation, and then you can also have this one is linear transition. You can also have a unicircle motion. Okay, unicircle motion, and it can be calculated by the angular velocity. Okay, and you can derive that. So you will have the speed is like this. Okay, this rotational speed is omega is your angular speed. Okay. Okay, and that parametric function, each one of them, your xy is formulated by t. So your xy is formulated by t. So this st yt is exactly your equation. Okay, and your omega is theta d theta dt. Your omega is angular speed, so it's d theta dt. So here it's building up your relationship between your positional change and your control variable theta and t. Okay, so that's that. And then you got your Jacobian metric. Okay, inverse Jacobian. Okay, so you do got the d and theta, right? And you do have a configuration space. Configuration space is the total space that you can set up your configurations. So you actually have a configuration space, a workspace. Workspace is the location your any vector can reach. Configuration space is the control variables space that you can set up using your control variables. Okay, so that's called configuration space. But anyway, configuration space is all of the possible setting that your robot can do. Okay. So now, what's the relationship of this Jacobian and your trajectory? So path is a sequence of robotic configuration in a particular order without regard to timing. So we don't care about timing. We just care about point A to point B as path. Okay. And trajectory is, we do want to know about the trajectory because we care about how smoothly my car can be driven from point A to point B. So I need to do trajectory planning. So path means that I don't care how I drive it, so I can ramp up all speed from point A to point B. But trajectory planning, you may want to ramp up your speed, keep it for a while, and then ramp down. Okay, but these two may go to the same location. Actually, it depends on different trajectory, and you may work on the same path, but using different trajectory. Okay. Okay, so path planning is that you want to generate your trajectory based on certain paths. Okay, so path is your destination that you want to go to. right? So you will input geometry of a moving object, okay, and the obstacle, and how your robot can move. And then you need to have the kinematics for the robots and the initial and the goal robot configurations, okay? Continue, that's your input. Your output is a continuous sequence of collision-free robot configurations. So output is your planning result. That would be your control variable that control you through the configuration space so that your robot can travel from the source to the destination. Okay, so this one, there are two things involved. Okay, so one thing is like, okay, one thing is that you have a robot arm. Okay, so you want to control this one to the pick up something. So there's an end effector's path and trajectory. There's another one that you do also have the wheel or tractor. You can move your car as well. So this one also has the point A to point B, traveling from there to there, right? So there's a vehicle problem, there's a manipulator problem. So vehicle portion is the movement of your robot location. Manipulation problem is your robot end effector to point, end effector point, some movement. These two are two separate paths. And sometimes these two paths also related to each other. So you need to have a robot computer to calculate both paths. Okay, so at least right here, when we talk about path planning, we just look at one path, one loop, okay, at a time. But when two loops together, you still need to have higher degree of calculation in order to plan it, okay? So turn a specify Cartesian space trajectory into, okay, that's a path E, okay, into appropriate joint position of reference value. Okay, that's a proper trajectory. Path planning is like just find out from point A to point B and how can you avoid the obstacles. Trajectory is that we need to control over the time, making sure that you have the right velocity and acceleration so you'll get to the point. Okay, so you do have path specification and path constraint. And then getting these two input, you get your joint space acceleration and speed. This one is to control your force because your F equals ma. Double derivation is your acceleration. Okay, and you also want to control your speed. Okay, that's a Cartesian space. Is that okay? Okay, so that's you try to use this one. So basically, you do want to come up with different profile for the control. Okay. So there are several different kind of portfolio for you to move on over time. Okay. There's a lot of equations. So here I try not to talk about this math too much. So basically, you try to come up with a math to control your path. Okay, and you can simulate your path. Let's see. Actually, here are a lot of math, but eventually they will become a control systems loop, feedback loop. Okay, you become control feedback loop, and that's the one we see it last time. That's the slides that we saw it last time when we had inverse differential kinematics. in a way, at the very end, the whole controlling is like this, okay? This D is your past specification. You want to go from somewhere. And this Q will estimate where you are. So the difference, you try to minimize the difference so that you will go on the path that you want to plan on. Okay. And the output of this control feedback loop is your state variable. Is that okay? It's your state variable. So that actually is the goal for this control. Okay. Is that okay so far? So this portion, I just briefly talk about the concept. Okay. Let's see. We have Sudhir. Okay, Sudhir, you have any question? No? No question? Okay. Anyway, we finish this the discussion for this one called pass. Okay, pass. So there are video, please watch it. Okay. Is what I just go over the basic idea. The basic idea for this trajectory and path is that path is the way, the location you want to travel to. Trajectory is how you go to there. Okay. And then trajectory is the real motion that you want to control. And you want to use your parametric function to control it. Okay. And then you set up your Jacobian and inverse Jacobian to solve the system of equation to get your desired speed, okay, for your control variables. That's the goal. That's the goal we have. And eventually those things can be formulated in a loop, feedback loop, okay? And these two can be put into two possible paths. One is your manipulator, that is one feedback loop. The other one is your vehicle. Some robots do use wheels. Some robots do use tractors. Some robots do use the legs. Okay, some robots have legs. So that control is totally different. Okay. Any question? Hello, any questions so far?
I don't think so.
Okay, if no question, we are up to here today, okay? And Friday, I'll still be here answering questions, okay, answering questions. So if there's a technical question, I try to explain. If there are sample code needed, I'll give you the sample code or explain the sample code, okay? And as you can see, these maths, none of them are easy, I know, but there's a problem. This Lewis University's course is 8-week course, right? It's an 8-week course. It's not even 16-week course. But some universities do have 2-semester robotics course, right? So 2 semesters, you get 32 weeks. And this one only 8 weeks. So it's actually way too short, way too short. So to teach this course very completely, actually, it's very hard. I talked to the Professor Dean before, okay, Dean and professors, other professors before that. I know it's very rushed, but I have no idea why. How can we change? Because I'm only a adjunct professor. Okay, so let's look at Berkeley EE 106. That's a 16-week introduction to robotics, and there is that's 1 semester, 16 week, and there's a EE 106B. So the whole robotics has 2 semesters. right? The whole robotics is 2 semesters, and 2 semesters we get 32 weeks. They get 32 weeks, and we are trying to squeeze them into 8-week accelerated course. So, I mean, we don't have that much time, okay? But we just try to give you some overview of each different module, what they are, okay? So going through the kinematic, going through the sensor, going through the different topic, give you the basic idea of each part of the robot, how can we do it, okay? But if you really want to get deeper, some courses like this 4 and 8 week is really too short, okay? Really too short. But then I don't want to be in this way, okay? Sorry for that. But they don't have the plan to change the 16-week or even 2 semester only. Any question? No? Okay, no question. That's it for today. Okay, see you on Friday if you have time. I just want to answer question if somebody has, okay? Okay, see you then. Bye-bye.